By the end of this video, you will be able to look at code like this and answer one question with confidence. How long will this object stay alive? Not in theory, but based on how the runtime actually sees it. I'm K1, welcome to my channel. In the previous video, we talked about memory shape, how objects connect to each other, and how that shape begins to form as code runs. In this video, we are looking at the same idea from a different angle, time. Lifetime is just memory shape that refuses to collapse. Same graph, same references, just stretched across time. Before we look at examples, just a quick recap on stack frame concept that we have already explained in the first video of this series. Every time a method is called, the runtime creates a stack frame. That stack frame holds parameters, local variables, and temporary references used by the method. When the method returns, the stack frame disappears immediately. Any references that lived only in that stack frame are gone. If an object was reachable only through those references, it becomes eligible for garbage collection. This is the baseline, and this is the default behavior. Everything we are about to see is just different ways a reference doesn't stay inside that frame. Here is when passing is harmless. We have just a method called process with one parameter. This reference to order lives only in the stack frame of the process. When the method returns, the stack frame is destroyed. The reference disappears, the object's lifetime is unchanged. Nothing escapes. This is cheap. This is safe. This is not a problem. Now let's look at a few examples when a reference escapes. When the object is stored, like as you see in this example. Here the reference is stored in a field. The object is no longer tied to the lifetime of the method. Its lifetime is tied to the lifetime of the container. Same object, longer lifetime. Here is another one. At first glance, this looks harmless, but the lambda needs access to order after process returns. A stack frame can't survive that. So the compiler rewrites the code. Conceptually, it becomes something like this. One class called closure that wraps around the order, and the order object doesn't move. It was already on the heap. What changes is the reference. It's lifted out of the stack frame and stored inside a heap allocated closure object. As long as the task is alive, the closure is alive, which means as long as the closure is alive, the order is alive. Nothing moved, nothing was copied, the lifetime just stretched. Now let's look at another one. This looks simple, but await splits the method in half. The compiler generates an async state machine and stores order inside it. The state machine lives on the heap. Even if the method returns immediately, the object stays alive until the async work completes. Async isn't the problem, time is. Same object, same code, different lifetime. So far, we have been talking about one object, but objects don't live alone. An order usually points to a customer, that customer points to addresses maybe, those addresses point to other objects. In memory, this isn't a single object, it's a graph. And when you extend the lifetime of one node, you extend the lifetime of everything it can reach. Here is a minimal example. Here is a class that contains a list. That list is static, which means it lives for the lifetime of the process. So what just happened? Not just the order stayed alive. The customer stayed alive, the addresses stayed alive, everything reachable from that order stayed alive. Not because you asked for it, not because you need it, but because reachability says it must. One reference quietly pulled an entire object graph into a longer lifetime. And this is rarely happen in one place. Real systems don't look like one method call. They look like this: controller, service, domain, cache, logger, maybe even different than this. Each layer receives the object. Each layer can store a reference. Each layer gets a vote in how long that object lives. And in the end, there is no negotiation. The longest lived reference wins. By the time the request is done, the object itself may no longer be needed, but the shape created around it remains. And memory only cares about shape. But why this turns into performance problems? None of those that we have discussed earlier are visible in code, but it becomes very visible at runtime. Larger object graphs survive longer. More memory accumulates in long-lived regions. Compactions become harder. Cache locality gets worse. Pauses get longer. Nothing here is dramatic on its own. It's the accumulation that hurts. Same objects, same code, longer lifetime. I'm not offering fixes here. I'm not saying those codes are wrong. This is about learning to see your code the way the runtime sees it. Once you see that, performance problems stop feeling random. I have one sentence takeaway for you. Let's read it together. In peace. If passing objects defines how long memory leaves, what actually forces the runtime to clean it up? What decides when garbage collection runs? And why does it sometimes feel unpredictable? That's what we'll talk about in the next video in this series. What really triggers the garbage collector in C#. Stay with me, grow with me. See you next video.